To start the second talk of this morning session, which will be done by Elmar Wagner. And as you can see, the title is the description of the Dolbeault-Dirac operator on quantized manifolds via the Bernstein-Gelfand-Gelfand solution. So,
thank you. So it will be probably a bit messy talk. I know I had problems with arriving with German Railway. Then I noticed it's only 25 minutes ago.
yes.
I prepared more, so I'm sorry for. So if I'm too fast, if you have questions, please ask. I'm sure it will be a bit difficult to understand, but Alessandro gave a perfect introduction. So the thing is, it's a continuation of Alessandro's talk. And as you have seen, we're talking about non-convex geometry. But once you go to representation theory, you won't see much difference. And that's basically the message of my talk. So in Kahn's non-convex differential geometry, so there's one of the important notion is, it's a spectral triple, which defines a Dirac operator. So viewing the Dirac operator as a natural first order elliptic operator, und wie man es from guessing or index theory, so it has topological information. Now if you go non-commutative, you would like, you have a non-commutative manifold defined by star algebra, and you would like to extract topological information. And one of the ways to do it is by index theory from something which is a generalization of the Dirac operator. So here's a very brief definition for how Kahn defines a Dirac operator. So it's a spectral triple, it's defined by a spectral triple. We have an algebra A is the pre-star algebra, H is the Hilbert space. So you can fuse this pre-star algebra as a subalgebra of the bound operators. B is a self-adjoint operator, and it has bounded operators with the functions. So A you can imagine as functions, maybe from a non-convex star algebra, but functions on a quantum space. And here you see it. A first order differential operator will always have compact. Will always have bound commutators because it acts on function. If it's a Dirac operator, you can just multiplication by the gradient. And for compact quantum spaces, you require that the resolvent is compact. So it has eigenvalues, it has these eigenvalues that go to infinity. Now, the classical example is the Dirac operator on a compact Riemannian spin manifold, and that's what we want to construct exactly on the examples from Alessandro on the irreducible complex manifolds. So the aim of the talk, which I probably won't have the time, is first thing is on the irreducible complex manifold, there is really a way that you can construct a Dirac operator, and it's what all the ingredients are already given. And it starts with a differential calculus, which Alessandro already introduced. So in non-convex geometry, the problem is we don't have coordinate charge. So, but we have, if you study quantum homogeneous spaces, we can use a lot of representation theory. Representation theory is always global. You don't need charge, coordinate charge, and that will work. And from those that have a bit experience with non-convex geometry, will know a lot of problems in constructing spectral triples. So once that works are the irreducible quantum flux manifolds. And I'm trying to explain for those that have experience why this class of non-commutative spaces really work. So one of the biggest problems is to compute the spectrum. The construction of a Dirac operator as done by Ulrich Krämer 20 years ago. And still there was a problem. Well, we know that is a Dirac operator, it has nice differential calculus, but only recently we are able to compute spectrum and to show that it's actually a spectral triple. Now, example we did is from the D series. The A series is simple and was done years ago. So the idea is So look at the classical Dirac operator, describe it by the representation theory, and where we are, and then deform the representation theory so that we get global expressions. Well, as I said, just using representation theory. So what we deform are Lie groups and the associated Lie algebras, and then we consider quantum homogeneous spaces. And the Dirac operator, which we will construct essentially as the same expressions, but if we use our invariant vector fields as derivations, put it in the formulas, and then we get the Dirac operator on certain quantum homogeneous spaces, not on all, on the good ones. So the good ones are the Hermitian symmetric spaces of compact type. So we take a, well, that's just a homogeneous space. We have a Lie group that we can deform. We have a subgroup. We know how to define a subgroup quantum group. And so G should be same symbol. There's a reason that why we use same symbol Lie groups, because and H, of course, is a closed subgroup. Then the Lie algebra decomposes in its Lie algebra of H, the quotient, and an additional bar. So for the Hermitian symmetric spaces, this is of course H is of course a sub-Lie algebra, but here we see the adjoint action acts on the additional bar, and by adjoint action it keeps it invariant. So if you look at connections on homogeneous spaces, we get a connection for free. This is the space, linear space N is at invariant under the action of H. So you have H gives the vertical decomposition, and here you have for free the horizontal decomposition. So this is the reason why constructing Dirac operators on Hermitian symmetric spaces, yeah, it's much easier, and that is the reason why the Dolbeault complex works and gives us what we are looking for, a first order elliptic differential operators. What we need, some additional structure in a product to get a Hilbert space, and the operator we are looking for is given by this delta bar and its adjoint working on the 0K form. So that works for the best for the irreducible flag manifolds. Here it's all classical. Now what we can do is here we can take a compact maximum compact subgroup. So then we decompose the Lie algebra in a Levi factor. You have two linear spaces, and one has a representation of the tangent space, and one has it's just exterior. Again, you have invariance. So for the irreducible type, we take out one specific symbol root, and then the tangent space is generated by the adjoint actions of the Levi type. Right? I don't know what's for back in, yeah, here you are. So what's important, this is an irreducible representation. So in this case, and this is an irreducible representation, you really get elliptic operators. So maybe I should, yeah, then, yeah. So this operator, and this is from the simple roots. The one we take out is the only one that acts non-trivially. The other ones are invariant, so they act on the orbits just trivially. Now we know once we have the tangent space, we can take wedge products of the tangent space or cotangent space, whatever. And these are the associated line bundles. Well, there's a notion in non-convex geometry how to construct them. We have the tangent space given by left invariant vector fields with the same dimension as in the classical. Well, yes, it's the classical, but in the non-commutative case, this survives the tangent vector. So it's left invariant vector field survive, and the delta bar operator has very simple expression. You just act with left and right vector fields, and here you have the basis. These are the basis of, one can say, one forms. And if you want to go a higher order differential calculus, that works with the Bernstein-Gelfand-Gelfand resolution. And I hope someone here is a specialist in this, because it's surprising. I found it in the paper from Heckenberger-Kolt. It's still a bit surprising that it works for in the quantum case. So here the deformation we have seen in the Alessandro storm, but I would like to point out the problems. When we deform these same symbol Lie algebra, the universal quantum enveloping algebra, there are elements, well, if you take the simple roots E, F, and some H. So one of these elements looks like an exponential. So this is something that should be in the group. And these are group-like elements. And that spoil a bit, well, that spoil a lot the theory. They do not act as vector fields. We don't have enough derivations in the deformation. Okay. So you have this relation you have seen. Now the relation, Alessandro didn't write the relation, but that's important. So if you take the symbol roots, the other roots you get by adjoint action. But in the quantum case, that won't work. So you just generate elements of higher and higher order in the quantum enveloping algebra. You get these are second order elements which represent something like, which should be actually vector fields. But here they look like a third order differential operator. And these things make the construction of Dirac operator, for example, on quantum groups, very, very difficult, not to say impossible. Well, there are ways, but they do not correspond to a nice differential calculus. So the rest is maybe not so important. Hopf structure, you have some co-product. It tells you how to, you see it's a tensor product representation. It tells you how to act on products, and here you see these are twisted representations. There appears some case. They are not derivations. And going to the now to solve all these problems that I mentioned in the deformation, we go to irreducible quantum flag manifolds. And you have seen the list from Alessandro, where he took some points out. These are the one that works. So the first thing is, you take a quotient. Well, the quotient I wrote like, these are the vector fields and something which is infinitesimal invariant. It's the same as taking the quotient with a group. Now, I told you these group-like elements are very, very bad. But we take them, we keep them in the Levy factor. So the functions we are considering, they are all invariant on these bad elements. Then on the invariant part, they act trivially. Now you would like to have derivations. If you act with the one that is one that we took out, the EJ. Now it actually acts as a twisted derivation because it has this action of this group-like element. But in the invariant elements, this is trivial, and then you get an honest derivation. So we have a great chance to get an differential calculus by derivations. On the irreducible, as we have seen, so this corresponds to one of the snot that Alessandro took out. And that is the only element now that acts really non-trivially. The tangent space is an irreducible representation. You can generate all the other left in one vector fields by just taking the adjoint actions. The adjoint actions, it's quantum adjoint actions, do not produce elements in the Lie algebra. They are of higher order, or at least they look at higher order, like here, like these are products. But if you act as this product, one of this factor acts on the functions, but the functions are invariant, they are zero. Here again, so this second, which looks like a second order differential operator, satisfies Leibniz so like a first order differential operator. So we are back in business, we get the right amount of derivations, and that allows us not only to construct the right differential operator, the first order differential operators, it allows us to define the Dolbeault operator. Now here, that's what I mentioned from this E0, you take that joint action, but in fact, it's like multiplying with the other elements. Course. Yeah, here we are. So we take this one. Actually, we should generate the tangent space by that joint action, and you would get again elements in the Lie algebra. In quantum doesn't work, but we get powers. And if you look at the CR relation, everything which is on the right, which is invariant, just gets killed, just acts trivially. Now, vector bundles, here we have the tangent space, the dual space we take as a form. This box you can think as associated vector bundles, but it tells you we can take tensor products and look at the invariant functions. You should know this from classical constructions. And the Dolbeault operator is, if you remember in one of the slides, which was still classically, it's the same formula. It still works. So, and it satisfies the Leibniz rule. So from here, from Dolbeault operator to the half part is completely the same formulas as in the classical case. You won't see a difference. So thanks to Heckenberg-Kolb, it's now more than 15 years. Now they show that these operators like these are unique. Yeah, here. They show the existence, they are unique, and they show that you have this higher order differential calculus, they have the classical dimension. But this paper is difficult to understand because it's made everything on representation theory and without very explicit formulas. But then I found a different paper, and I was surprised. So they found a quantum version of the Bernstein-Gelfand-Gelfand resolution, which is surprising that it exists. And here's a classical Bernstein-Gelfand-Gelfand resolution. So if you look at this, there's a lot of antisymmetration. So you take commutators. Now these commutators, as I told you, these commutators do not exist. These do not give elements in the Lie algebra. But in the case of the irreducible flat manifold, there you have this decomposition. That we get, so the commutators live in B, in the invariants. So these commutators, which are not actually in quantum commutators, act trivially. We just can kill them. For the irreducible case, all these things don't appear. And if you keep the first line, this gives you still a Bernstein-Gelfand resolution. This is a quantum Bernstein-Gelfand-Gelfand resolution. Much simpler because all the other complicated terms disappear. And from this, we can construct, well, here it's written, the Heckenberg-Kolb, so they have a complex. It's actually, if you put the augmentation like it's an exact sequence. We don't need all these antisymmetrization. We have here just multiplication that we can do in the quantum case. Dualizing, we get the associated. I was talking about getting forms by considering associated vector fields. So we get everything for free. We get the Dolbeault operator, we get the forms, we get the actions. What we need now is Hilbert space and adjoints. And if you want to compute the spectrum, well, we need explicit construction to be able to construct the spectrum. So not much time. So that was prepared for a much longer talk. So here it's done. On this slide, I'm just telling you, in this example, everything can be done. Here you see again. Actually, we should take for the left-hand vector field adjoint actions, but that doesn't matter too much. It's enough to take products. Getting all this close. And here's such products. Yes, if you take this is a serialization, so you would need to get the left-hand vector field. You would have to take the adjoint action, but you get that looks like a first-order differential operator, but it's not, because all these versus EQs act as zero. This is all done. So to keep the information short. So we have the same classical dimension. We can take associated vector bundles. We have the forms. We have the BGG resolution. We dualize, and then you have the operators acting on from 0 k forms to 0 k plus 1 forms perfectly. And this is differential calculus because this is an exact sequence. Again, associated bundles. You know it classically. So again, everything is classical. You see that it's a you have the cotangent space. You take the batch product, and then you have two times such product is a line bundle again. It looks like this, but you have to take these matrices act in the tensor product with the group. But thanks to the Bernstein-Gelfand-Gelfand resolution, it keeps these associated line bundles invariant. So in a product, well, one can try to define a Hodge star. It works. Riemann did it. But since I know how it should look like, so I just put it by hand by the Haar measure, then it works. So I mentioned that in our case, because irreducible quantum flat manifolds, our quantum tension space act as derivations with twisted derivations, but this is just some factors which is bounded. So immediately we get bounded commutators. This was one of the conditions for spectral triples. Then to find the spectrum, first we need to decompose our forms into representations of the Levy factor. So that works with the branching laws. This is a lot of work that has to be done. It's a low-dimensional example. So here you see what we did. Since it's a low-dimensional example, we need to find highest weight vectors. Maybe here you see, well, there's a Bernstein-Gelfand-Gelfand resolution. It's a Wehrmann module that goes from the top form, goes down, 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 and then here to the trivial ones. Dualizing, we go up, up, up. Now, if you want to know, we know what we need are highest weight vectors of the Levy factor. So things that move to the right, in zero, it's in the kernel by action to the right in the kernel. These are highest weight vectors, and these can be calculated. Calculated them. Well, here's are the multiplicities. Here are where we got very explicit representations. These U, I, J as a individualization as a matrix coefficient on the group on SO5. So the QT form doesn't matter, but you can think about the fundamental representation, the matrix functions. So these are very explicit realizations, and even more, since we are using representation theory, all which we need to know is highest weights. So once we know the highest weights, we get an isometric, we get unitary equivalence to the forms. I take highest weight, I can write down here the forms. So all we need, you don't need to work on forms. We can make the computation on highest weights. Where was it? Here. So And we get new differential operators that work only on highest weight vectors, which are elements in the group by the Peter-Weyl theorem. Well, these projections come out immediately to make the Bernstein-Gelfand resolution a resolution. These come out immediately, projections, but they are completely algebraic. These are orthogonal projections, also they are not star invariant. So for the adjoint operators, is a problem just taking the star. If you take the star in the, or yes, it's a star missing from the Lie algebra, the real structure, our tensor products are not invariant. You need to put here the projections. There's another way to do it. If you could really compute the inner product, we don't need the projections. But this is a little trick. So to express these projections by algebraic expressions, so we can compute the spectrum by just acting with invariant vector fields on highest weight vectors. And that's what we did. And after a lot of computations, this is the result. So here you see, I just take highest weight. That's all I need. And I even better, you have a exact sequence. So there's the highest weight are one-dimensional or two-dimensional. So first we computed Laplacian on the one-dimensional vector spaces. And then just by decomposition, we get the eigenvectors of the Dirac operator, where there are some vector from highest weight space, two-dimensional highest weight space is involved, but we don't care because we just take the action of the operator, so we get an eigenvalue. And the same we do again with the other highest weight vectors. And here's a list of the eigenvalues. Now these square brackets are the so-called Q numbers. If you take a limit Q to 1, you will get the natural number n just by the derivative. And here you get, well, here again. So these type of Q numbers come if you deform the Lie algebra and look at the representations. So if you know that your coefficients in the representation theory, it's quite naturally that you always appear these deformed numbers. Now I never looked at the spectrum of the classical Dirac operator on these homogeneous space, but my guess is that this is really the same numbers. If you take, if you ignore the square brackets and put natural numbers, I guess it's the same spectrum. If someone knows the spectrum of these manifolds, it would be grateful if you can give me some reference they can compare. And this is just because I didn't like to work with Schwarz star operators. So these are just parametrizations. These are scaling operators. They are not very important. Multiplicities, again, it's the same. It's a Y formula. So I'm very confident that this spectrum, in this special case, and probably in all the other cases, it's very similar to the classical case. So now it's time to. Thank you for your attention.